Many real-world scenarios are modeled with various equations and formulas. They often have multiple variables. Sometimes we'll want to isolate a variable so that we can highlight the relationship of all the other values to that variable. For example, if we take the formula for the area of a rectangle, area equals length times width, right now the area, which is represented by A, is isolated. But we can rewrite the equation with a different variable isolated, such as L. If we divide both sides of our equation by W to get L by itself, we can see how we get the equation L equals A divided by W. So when we're isolating a quantity in an equation, once we have the equation, whether we're given it or we need to translate it, we want to use our addition and multiplication properties on both sides of the equation to isolate the desired quantity. We want to make sure that there's only one of that quantity and it is by itself. So we'll go through a few different examples on how to isolate. So first one, we have a physics student who uses the formula E sub k equals 1/2 mv squared to calculate the kinetic energy in joules E sub k of an object with a mass m kilograms traveling at a speed of v meters per second. Sometimes when we have these very wordy problems and you're losing track of what all the variables are, it might be really easy to skip to the end and see what is the question asking for. And see, is it important that we know what all the variables represent, or is there something simpler we can do? Well, we see the phrase, what is V, in terms of everything else. That just means to isolate V. So we need to get V by itself. So we'll take our equation, E sub k. Now, E sub k is one variable. It's not two variables. We're just using a subscript, and it just denotes kinetic energy. And we know that because it says kinetic energy is E sub k, mv squared. So we'll want to get rid of any other terms. There's no other terms on this side of the equation, so then we can get rid of any other factors that are being multiplied by v. So we have 1/2 and we have m. So we can multiply both sides of our equation by 2. That gets rid of our fraction. 2e sub k equals mv squared. And then we can go ahead and divide both sides of our equation by m to eliminate the factor variable m, giving us 2e sub k over m equals v squared. And then last but not least, to get rid of the exponent, we square both sides. So v equals the square root of 2ek divided by m. And since we used our square root property, then it is plus or minus 2 times ek divided by m. Here again, we've got distance and traveling. Write the equation that gives time in terms of distance and velocity. Well, we're going to have to translate our own because they didn't give it to us. So distance traveled by an object moving at a constant velocity is found by multiplying the velocity of the subject times time. So distance is velocity times time. And so we can substitute our variables in. And it's asking us to isolate t in terms of d and v. So with d equals vt, well, to isolate t, all we have to do is divide both sides by v. So t equals distance divided by velocity. We're given another formula with a lot of information about the formula. What is r in terms of v, h, and pi? So we just need to get r by itself. V equals pi r squared times h. Well, to get rid of the coefficients of pi and h, we can divide both sides by pi and h. So r squared equals v over pi times h. And then we can square root both sides to get rid of the squared. So r equals the square root of v over pi times h. Now, radius can't be negative, so we will just leave it as the principal root. Here we have an equation that deals with gravitational forces between two objects. And when we skim through it, we see it's asking for what is d in terms of the other variables. So we just need to get d by itself. So we start with our formula, F equals g times m1 times m2 divided by d squared. So first, let's get d squared out of our denominator. We multiply both sides by d squared. So we're left with d squared times F equals big G times m1 times m2. Then we need to get rid of this F. So we'll go ahead and divide both sides by F. And we have d squared equals big G m1 m2 divided by F. And then we finish with a square root. Distance equals the square root of big G m1 m2 divided by